What's up, everyone? Welcome to my channel, and today, I want to talk about the biggest shift I've seen in the trades for the last couple of years in North America. The move to net zero buildings and how it's making hydronics the most important system in a modern home. Today, buildings are changing. Energy codes are stricter. Cities are banning gas. Clients are asking for low energy and net zero buildings. The big question is this: how do we design HVAC systems that are electric, efficient, resilient, and still comfortable? The answer is modern hydronics. For decades, we built homes that leaked air like a sieve, and we solved it by blasting them with 180-degree water from a fossil fuel boiler. A typical 2,500 square foot home 50 years ago needed 75 to 88,000 BTUs of heat. The game has changed. Today, that same home, built to energy standards like LEED or R 2000, has heating loads in the 10 to 15 BTU per hour per square foot range. That's 1/3 of the old requirement. The twin pressures of decarbonization and electrification mean we are shifting away from natural gas and oil. We're moving to electric heat sources like air-to-water and water-to-water heat pumps. And this brings us to why hydronics is the future. Before we go further, let's clear up what net zero actually means. Net zero does not simply mean adding solar panels. A net zero building is designed to dramatically reduce loads first, then meet those reduced loads with on-site renewable electricity. Modern net zero buildings share a few critical characteristics: high-performance thermal envelopes, very low heating and cooling loads, mechanical ventilation with heat recovery, all-electric systems, usually heat pump-based. As I mentioned earlier, today's buildings operate at roughly 1/3 the heating load of older homes. Why hydronics when in low-energy buildings or net zero buildings? When loads are low, comfort becomes the dominant design driver. Hydronic systems excel here for several reasons. First, superior thermal comfort. Radiant systems, like low thermal mass radiant panels, heated ceilings, or panel radiators, provide a gentle, even warmth. This is because you are warming the surfaces, not just pushing hot air around. 2. Acoustical comfort. A properly designed hydronic system using panel radiators can operate with virtually no detectable sound in the occupied space. Your heat pump's compressor is outside or in a mechanical room. No roaring furnace. No noisy fan coils interfering with your TV or conversations. 3. Insane distribution efficiency. Water is an incredible heat conveyor. It can absorb almost 3,500 times more heat than the same volume of air. This means you can move the same amount of heat through small PX tubing that you'd need massive ducts for. The electrical power needed to run a high-efficiency circulator is often a fraction of what a forced air fan requires. The math is simple. High distribution efficiency equals less electricity used. 4. Easy, precise zoning. Low-energy homes are very sensitive to internal gains. Hydronics allow room-by-room zoning by using thermostatic radiator valves, manifolds, low-power ECM circulators, all without large ductwork. Modern hydronics pair exceptionally well with electric heat pumps, which are essential for net zero buildings. Let's dig into heat source types. 1. Air-to-water heat pumps. These systems produce hot water up to approximately 130 degrees Fahrenheit, provide chilled water for cooling, operate efficiently even below 0 degrees Fahrenheit outdoor air. 2. Geothermal water-to-water heat pumps. This offer even higher seasonal efficiency. No outdoor equipment, long service life, but with higher upfront cost and site limitations. 3. Electric boilers. Electric boilers can still make sense for very small, ultra-efficient homes as backup or supplemental heat. But remember, coefficient of performance equals 1.0 for electric boiler, whereas heat pumps typically deliver 2 to 4 times more heat per kilowatt hour. Heat pumps, unlike traditional boilers, don't generate extremely high temperatures. They work best, and their coefficient of performance is maximized when they deliver heat at a lower temperature, say 120 degrees Fahrenheit, and work between the manufacturer's specified ambient temperature range. That is the sweet spot for modern hydronic emitters. This single piece of equipment handles all your space heating, space cooling, and often your domestic hot water, making the whole system incredibly resilient and versatile. Here's where hydronics really dominate. Moving heat with water requires a fraction of the energy needed to move it with air. In cooling mode, this matters even more. Every watt used by a blower becomes unwanted heat inside the building. Hydronic circulators often run at 10 to 30 watts. That's why chilled water fan coils and radiant cooling are so effective in low-energy buildings. Successful net zero hydronic systems share a few core principles: low water temperatures, simple piping layouts, buffer tanks for variable capacity heat pumps, high-performance emitters integration with HRV or ERV systems. This is not about complexity. It's about simplicity, repeatability, and resilience, exactly what modern hydronics were designed for. The bottom line is this: the low-energy and net zero revolution demands a change in how we heat and cool our home or the apartment. Hydronic system, paired with modern heat pump technology, is the only system that meets all those demands. Are you building or renovating a home to net zero standards? Let me know your biggest challenge in the comments. And if you want more deep dives into the future of HVAC technology, make sure you hit that like button and subscribe so you don't miss the next video. Thanks for watching, and I'll see you on the next call.